We've saved the very best of descriptive statistics for last. Variation in data, as in all things, is the spice of life, and it is the most interesting aspect. Variation in data are the differences among observations that gives clues upon which to make inferences. While we may be searching for the mean value of a population, it is the variation in the sample observations that will be the basis of our final understanding of how good our inference is. Imagine that 90% of all observations in a sample that you took are the same number. There is very little variation in this sample. We could conclude that the mean of this sample, the sum of all values divided by the sample size, is a very good estimate of the mean of the population, simply on the basis of the variation, or lack of variation, in the sample. And we would be right with this conclusion. It cannot be emphasized enough that all statistical inferences are ultimately based on variations in the data. There are several measures of variation, and each has its own place in statistical theory. Without dispute, the most important is called the variance, what we've been calling, informally, spreadness. Formally, this measures the variation about the mean. All variation must be measured from some specific point, and in this case, it is the mean value. And this is why the mean shows up in the formula to calculate the variance, which we will discuss below. Again, recall the difference between a population and a sample taken from a population. The convention of using the Greek letter sigma for the population parameter and the Roman letter s for the sample parameter is followed here, as it was when we developed the calculation of the mean. The small case Greek letter sigma squared is a symbol to designate the population variance. It is simply its name in shorthand and should not be confused with the capital Greek letter sigma, which we discussed earlier. The capital sigma, used before, is a mathematical symbol which tells us to do something, a mathematical operator. Have a look at the population formula for the variance. Mu is a population mean. The xi's are individual observations, data points, and capital N is the number of observations in the population. We see that the variance, sigma squared, is really the sum of squared differences between each observation and the mean. That is to say, measures how far the observations vary from the mean. The mean, therefore, is our point of reference. Now compare this formula to that one for the sample variance. We see that in this case, the variance is the sum of the squared differences from the sample mean, x bar. This is the case because, of course, we do not know the population mean. We only have a sample of the total population. We substitute the sample mean for the population mean. The xi's are individual observations, data points, and n, small n, is the number of observations in the sample. As the formulas show, the deviation from the mean are squared for both the case of the population and the sample. This has the effect of placing greater weight on values that deviate further from the mean. The further away an observation is, the greater the value in the formula, and thus the higher the variance. One or two observations that deviate substantially from the mean will have a dramatic effect in increasing the variance, because the power of squaring a number. 10 squared is 100, but 100 squared is 10,000. Note also that the formula for the variance of a population is different from the sample for a second reason. For the population variance, we divide by capital N, and for the sample, we divide by small n minus 1. The reason is that for a sample, we do not know the true population mean mu, and we are required to substitute. Thus, we have used up one of the observations in the calculation of the sample mean and cannot use it again. This is called the degrees of freedom in the estimate and will play an important role later. Because the values of x are squared in the formula, the units of measurement of the variance are in squared terms. Years squared in our example of animals' ages. To be useful, the standard deviation is computed simply by taking the square root of the variance. The population standard deviation is therefore sigma equals the square root of sigma squared. and its sample standard deviation is S equals the square root of S squared. Remember from the formulas that the population variance was called sigma squared and S squared for the sample. This will convert the units of measurement back from the original units of the data, from years squared for variance and back to years for the standard deviation in our animals' ages example. The ability to see a data set with nothing more than its standard deviation is amazing. If the standard deviation is 0, we know that all observations have the same value. They're identical, and they have no variation. Remember, if we know the standard deviation in figure D is, say, 100, then we also know that the standard deviation for figure C must be less. The observations in figure C are more homogeneous, are more like one another than those in figure D. The ages of students in your statistics class are much more alike than the ages of all the people in town. The variances, and thus standard deviations, for the classroom ages would be smaller than that for the whole town, which includes people who are elderly and babies as part of the whole group. In an important way, the standard deviation is a measure of sameness. It can be also thought of as a measure of differentness. How unusual is it for a baseball player to hit 70 home runs in a season? How many standard deviations is 70 away from the mean, the average, number of home runs hit by other players? The standard deviation will give us an answer to this question. As you get more familiar with statistics, you can begin to use the standard deviation as a measuring tool the same way you would use a ruler or a tape measure. I can say to you that I saw a wonderful movie last night, that it was a 1.5 standard deviation movie. This would be a very unusually good movie because the probability of going to a better movie is very small. We will talk about this in more detail in the probability unit coming up. One last note. Because the variance, and therefore the standard deviation, is measured as deviations from the mean, these two descriptive statistics are independent of each other. That is to say, two very different data sets may have the same mean but different variances, or the same variance but different means.